Have you ever stopped to think about what keeps the heart of the internet actually beating? I'm not talking about websites or apps, but the super complex hardware that's humming away deep inside data centers. Today, we're going to pull back the curtain on one of the unsung heroes of that world, PLDM, which stands for Platform Level Data Model. It's a protocol that works completely in the background, but honestly, without it, our digital world could just grind to a halt.
Okay, so imagine a modern server. It's not just one computer, right? It's more like a living ecosystem of all these specialized components, and each one has its own little brain, its own firmware. Now, trying to update all of them at once, that's like performing open-heart surgery while the patient is running a marathon. One slip-up, one tiny error, and the whole system could face a catastrophic failure. So how do you manage a high-wire act like that? Well, that's the exact problem PLDM for Firmware Update was designed to solve.
So here's our game plan. We'll start with why this is such a big deal in the first place. Then we'll meet the key players and the, let's call it, precious cargo they're handling. After that, we'll walk through the whole dance, the initial handshake, the actual data transfer, the super important verification step, and finally, that moment of truth when the new firmware goes live.
All right, let's kick things off by really digging into why this is such a tough nut to crack.
You know, the stakes here are incredibly high. A failed update doesn't just cause some small glitch, it can bring an entire mission-critical system crashing down. And that's exactly why this whole process is governed by a very rigid, methodical state machine. You can think of it like a pilot's pre-flight checklist. You can't move to the next stage until the current one is 100% cleared. It's all about guaranteeing a safe and reliable update every single time.
So now that we get the problem, let's meet the key players in this little drama. The best way to think about this is like a high-security delivery service. You've got a dispatcher, a secure warehouse, and a very, very special package.
On one side, we have the update agent, or UA. This is our dispatcher. It's the piece of software that kicks off and manages the entire update process. Then, on the other side, we've got the firmware device, or FD. This is our secure warehouse, the actual hardware, like a network card or a storage controller that's waiting to receive and apply the new firmware.
Before a single byte of firmware even thinks about moving, the update agent carefully inspects the package header. This is the shipping manifest. It gives a bird's-eye view of the whole update, what's inside, how big it is, and how many different components it's meant for. This is checkpoint number 1.
Diving a little deeper, we find the device descriptors. So if the header is the manifest, these are the super detailed packing lists. They have these hyper-specific hardware IDs to make absolutely sure the firmware is only delivered to the exact component it was built for. This step is just crucial for preventing a complete disaster. And finally, every package comes with a tamper-proof seal, the checksum. The update agent runs the numbers on this mathematical signature before anything else happens. If the numbers don't match up, it means the instructions themselves are corrupt, and the whole operation is stopped right there in its tracks. This makes sure the process is sound from the very beginning.
All right, so the package manifest has been checked out, everything looks good. Now it's time for our dispatcher and the warehouse, the UA and the FD, to have a little chat.
This is not a blind delivery. The update agent sends what's called a pass component table command. It's basically asking, hey, I've got this specific update for you. Are you ready for it? Can you accept it? The firmware device then takes a look at the request. It might say yes, or it might say no if, for instance, the new version is actually an older one and downgrades unallowed. Only after we get a thumbs up does the process move forward to the ready exit for state.
And now, for the main event, moving the actual firmware data.
And here's something really cool that shows why this whole process is so tough. The transfer is a pull process, not a push. The firmware device is in the driver's seat here. It sends a command asking for the next chunk of data. It takes that chunk, processes it, and only when it's good and ready does it ask for the next one. This methodical, back-and-forth conversation makes sure the device never gets overwhelmed with data. It keeps the transfer stable and totally reliable.
Once that loop is all done and the very last piece of data has been sent, the UA sends a final transfer complete command. This is the crystal clear signal that the delivery is finished, and it's time to move on to the next critical phase.
So, the package has arrived. All the data is there. But we are far from done. Now comes the really intense inspection phase inside our secure warehouse. The transfer might have been successful, but is the firmware itself actually any good? The firmware device now runs its own deep verification on the complete image it just received. It's scanning for any data corruption, it's validating security signatures, and it's confirming version compatibility. This independent check is an absolutely essential last line of defense.
And the firmware device doesn't just give a simple yes or no. It sends back a verify complete command with a very specific result code. 0 means success, of course, but a failure gives you a reason. Maybe a security check failed, maybe the process timed out, or there could even be a vendor-specific issue. This detailed feedback is so important for figuring out what went wrong.
Okay, this is a really important question. What happens if the FDD actually finds a problem? Does the whole thing just crash and burn?
No, not at all. And this is the beauty of it. The entire protocol is designed to fail safely. If the update agent gets any kind of failure code back, it immediately issues a cancel update component command. The firmware device then just completely throws away the faulty firmware and goes right back to its original stable state. The old working firmware is never, ever compromised.
Okay, so the transfer was a success. Verification passed with flying colors. The new firmware is staged and it's ready to go. It is time for the final, decisive step.
This is the moment of commitment. The update agent sends the activate firmware command. This is the final instruction, telling the firmware device, okay, make that new, fully vetted firmware active. This really is the point of no return. And this activation can happen in a couple of ways. With self-contained activation, the device might just pause for a second, apply the update, and come right back online. But what you see more often in big servers is activation on reset. In this case, the new firmware is locked in, but it only becomes active after the next reboot. This is a brilliant feature because it allows for planned downtime and perfectly coordinated updates across an entire system.
So, what's the big takeaway here? PLDM gives us a highly structured, multi-stage process that turns a potentially very risky operation into something safe and predictable. Its clear command and response dialogues, combined with really robust verification and error handling, mean that even if something goes wrong, the system stays stable. This is what makes reliable firmware updates possible, even at a massive scale.
You know, PLDM is a perfect example of a foundational protocol that most of us never even see, yet it's absolutely essential for keeping our digital infrastructure humming along. It kind of makes you wonder, what other invisible, highly structured protocols are out there, quietly making sure our complex world doesn't just fall apart?